Everyone says the moon is natural. But then why does it vibrate for hours when hit? Why is its size, orbit, and position almost perfectly engineered for Earth? Why do official measurements raise questions no one wants to answer on camera? Hidden in decades of data are patterns that don't fit simple explanations. Astronauts recorded strange signals. Scientists quietly disagreed. And some files were buried for years. What if the moon isn't just a rock in space, but the greatest structure ever discovered? The month the moon became measurable. In July 1969, the moon shifted from a distant light to a place with coordinates, schedules, and paperwork. NASA's Apollo 11 mission lifted off from Kennedy Space Center in Florida on July 16 and reached lunar orbit 3 days later. On July 20, Neil Armstrong and Edwin Buzz Aldrin landed the lunar module Eagle in Mare Tranquillitatis, a basalt plain that had been mapped in photographs for years and then chosen through committee decisions and flight constraints. Michael Collins remained in lunar orbit in the command module Columbia. The landing was followed by small, practical actions that turned the surface into a work site. A television camera set on a tripod, a contingency sample collected early, a flag assembly pressed into regolith, and instrument packages carried a short distance from the landing gear. The mission returned with physical material rather than impressions. Apollo 11 brought back about 21.5 kilograms of lunar rocks and soil. Scientists who had argued about what the moon might be made of now had sealed sample boxes to open in controlled rooms. In Houston, the Lunar Receiving Laboratory processed those materials with a chain of custody routine that resembled forensic work. Early descriptions were restrained. Basalts and breccias were logged, weighed, photographed, and subdivided. The main new fact was not a single striking specimen, but the existence of a repeatable chemical and mineral record that could be compared to Earth rocks using the same instruments used for terrestrial geology. The shift toward measurement had started before any landing. Soviet Luna 9 made the first soft landing on the moon in February 1966 and transmitted panoramic images from Oceanus Procellarum. In the same decade, the United States flew Surveyor landers that returned close-range photographs and tested soil-bearing strength with simple mechanical touches. These machines did not add drama to the moon. They replaced older fears and older guesses with specific data, like the angle of boulders, the texture of dust, and the way light behaved across small ridges. Each mission created a layer of documentation that later planners relied on, including the Apollo teams who chose where a human crew could land and leave again. Apollo 11 was followed by a run of missions that treated the moon as a field site. Apollo 12 landed in November 1969 and retrieved parts of the earlier Surveyor 3 spacecraft for analysis, a small act of hardware archaeology done within a few hours of EVA time. Apollo 14 reached the Fra Mauro region in February 1971. Apollo 15 landed near Hadley-Apennine in July 1971 and introduced a lunar roving vehicle that extended human travel beyond walking distance. Apollo 16 went to the Descartes Highlands in April 1972. Apollo 17, the last crewed landing, reached Taurus Littrow in December 1972, placing Harrison Schmitt, a trained geologist, on the surface alongside Eugene Cernan. The mission transcripts read like field notes punctuated by radio checks, not like declarations. The voice traffic often focused on sample numbers, orientation marks, and whether a rock had a friable rind. A set of instruments installed during these missions produced one of the most enduring lunar datasets. The Apollo Lunar Surface Experiments package included seismometers, heat flow probes, magnetometers, and retroreflectors. The retroreflectors were passive devices that enabled lunar laser ranging, where pulses of laser light from Earth observatories are reflected back to measure the Earth-Moon distance with high precision. The seismometers recorded vibrations from natural events and from deliberate impacts, such as spent rocket stages guided to strike the moon after crews departed. Those records demonstrated that the moon experiences moonquakes and responds to impacts with long-lasting vibrations compared to many Earth settings. The data were published and reanalyzed over decades, and the underlying fact remained stable. The moon has a measurable internal structure with seismic properties that can be modeled from real signals rather than from analogy. The rock samples also anchored the lunar timescale. Radiometric dating placed many basalt flows in the range of billions of years, with highland materials often older than Mare basalts. The chemistry showed patterns that were not arbitrary. Compared to typical Earth crustal rocks, lunar samples were generally low in volatile elements, and many contained a northosite associated with a primordial crust. These outcomes were written up in scientific papers and consolidated in reference works used by planetary geologists. The results did not require imaginative framing. They required careful lab work, calibration standards, and agreement on how to interpret isotopic ratios under known assumptions. Alongside the laboratory work ran a parallel track of public interpretation that did not follow the same caution. The idea that the moon might be artificial did not originate with Apollo, but the Apollo era gave it a new vocabulary. In earlier centuries, writers had already treated the moon as a stage for manufactured worlds. That tradition carried through the 20th century in fiction and in popular essays. A 1,970 book by Vasin and Sherbakov in the Soviet Union is often cited in later discussions for treating the moon as a constructed object. Though its claims did not enter mainstream planetary science, in the United States, the phrase, "Who built the moon?" circulated in public conversation long after Apollo ended, sometimes detached from any particular author and sometimes tied to later popular works. The persistence of the phrase became a sociological fact. Some topics remain alive because they are easy to repeat, not because they are supported by new measurements. Certain real observations were frequently lifted out of context and reused in those conversations. The moon's low average density compared to Earth was described as an oddity, even though density alone does not specify composition in a unique way. The moon's large relative size compared to its primary planet, when contrasted with other moons in the solar system, was presented as unusual, while astronomers treated it as a boundary condition for formation models. The long ring of impact basins and Maria visible from Earth was sometimes described with architectural language, even though those features were mapped as geologic structures shaped by impacts and volcanism. The practice of giving Maria Latin names, established in early lunar cartography, occasionally added a sense of intention to features that were named for convenience and tradition. During the Apollo missions, some astronauts did describe the moon in memorable terms in press conferences and debriefs, and those remarks traveled widely. Short lines were repeated because they were compact and human. In technical records, the same crews spoke in procedural phrases, returning again and again to step-by-step tasks. That contrast between public interviews and mission audio became another real ingredient in later myth-making. The transcripts show engineers and astronauts working to avoid errors, fix minor issues, and preserve data. The public remembered a few lines and a handful of photographs. The post-Apollo decades expanded lunar observation without crews. Clementine, launched in 1994, mapped the moon in multiple wavelengths and produced gravity inferences through tracking. Lunar Prospector, launched in 1998, detected enhanced hydrogen signatures near the poles, consistent with possible water ice in permanently shadowed regions, a result that later missions refined. Japan's Kaguya orbiter, launched in 2007, returned high-resolution imagery and gravity data. NASA's Lunar Reconnaissance Orbiter, launched in 2009, produced detailed maps and photographed Apollo landing sites, including tracks and hardware, offering a kind of archival confirmation through modern cameras rather than through argument. China's Chang'e program added landings and sample return, including Chang'e 5 inches 2020, which brought back new material from a geologically younger basalt region. Across these decades, the moon became more precisely described without becoming simpler. Measurements accumulated: topography, gravity anomalies, crust thickness estimates, surface composition maps, and thermal properties. Each dataset included margins of error and competing interpretations. Scientific writing continued to describe what could be defended and to separate observation from inference. Public writing continued to favor tidy sentences that sounded complete. Two parallel records existed at once, one of instrument readings and one of cultural shorthand. In archives, the moon's modern history is a sequence of dated missions, tracked communications, published datasets, and preserved samples catalogued by number. The narrative formed by those records is quiet and administrative. A place was visited, instruments were installed, and measurements were taken again and again under different constraints. The moon's surface became a repository for human hardware and for human documentation. with coordinates attached to each object. The physical moon did not change because of those records, but the way it could be discussed changed, as the range of verifiable statements expanded. The measurements that refused to stay simple. Long before most lunar data appeared in scientific journals, it passed through filing systems, scheduling boards, and internal monitoring routines. Engineers and administrators treated the moon as a remote installation that required constant oversight. Transmission windows were planned weeks in advance. Equipment performance was logged daily. Storage systems were designed to preserve signals that might not be interpreted for years. From this point onward, lunar exploration became centered on continuous recording rather than brief human presence. One of the earliest long-term systems was the passive seismic experiment. Beginning with Apollo 11 and expanded by later missions, a network of seismometers operated on the surface until 1977. By 1971, 4 stations were functioning simultaneously. These instruments converted ground motion into electrical signals and transmitted them to Earth. Processing centers separated background noise from identifiable events. Each signal was catalogued with time markers and location estimates. Over 8 years, thousands of records were compiled. The data revealed several forms of lunar seismic activity. Shallow moonquakes originated within the upper mantle and appeared related to internal stresses. Deep moonquakes occurred at greater depths and followed regular tidal patterns. Thermal quakes were linked to surface temperature changes at sunrise and sunset. Artificial impacts, produced when rocket stages were directed into the surface, created controlled reference signals. These events allowed scientists to model internal layering and estimate crust and core properties. A recurring observation was the prolonged duration of vibrations. After strong impacts, oscillations sometimes lasted for more than an hour. Laboratory studies and theoretical models associated this behavior with fractured rock, low internal temperatures, and the absence of water. These conditions limited energy loss. The finding was documented in technical reports and conference proceedings and became a standard feature of lunar geophysics. Gravity measurements developed in parallel. During Apollo tracking operations, engineers noticed small deviations in spacecraft motion. These irregularities indicated uneven mass distribution. Subsequent analysis connected them to dense regions beneath major impact basins. Later missions refined these observations. Clementine and Lunar Prospector improved resolution in the 1990s, producing more detailed gravitational models. The most comprehensive gravity survey came from the Grail mission launched in 2011. 2 spacecraft orbited in close formation and measured changes in their separation caused by gravitational variations. The resulting maps, released in 2013, revealed buried structures, basin boundaries, and crustal thickness differences. These datasets were combined with topographic information to construct interior models. Grail results showed that many Maria overlie dense subsurface material. Numerical simulations demonstrated how ancient impacts thinned the crust and promoted volcanic flooding. Similar patterns were compared with data from Mars and Mercury. The Moon's gravity field appeared complex, but consistent with established physical processes. Independent teams confirmed the main findings. Laser ranging provided another continuous measurement record. Retroreflectors, installed by Apollo missions and Soviet rovers, enabled distance measurements between Earth and Moon. Observatories in several countries conducted these experiments. Each session involved firing thousands of laser pulses and averaging return times. Corrections were applied for atmospheric effects and instrument drift. Over decades, these observations showed that the Moon is gradually moving away from Earth. The average rate is about 3.8 centimeters per year. This recession results from tidal interactions that transfer rotational energy from Earth to the Moon's orbit. Geological evidence from ancient sediments supports this process. The measurements are included in planetary navigation systems. Laser ranging also supported tests of gravitational theory. By comparing observed lunar motion with theoretical predictions, physicists evaluated possible deviations. Within experimental uncertainty, the data matched general relativity. Thermal measurements added further constraints. Heat flow probes deployed during Apollo 15 and 17 recorded temperature gradients beneath the surface. Installation difficulties affected some readings, but corrections were applied. The data indicated low internal heat production. This suggested limited ongoing geological activity. Later orbiters expanded thermal mapping through infrared sensors. Surface temperatures were measured across different latitudes and lighting conditions. Permanently shadowed polar craters exhibited extremely low temperatures, allowing volatile compounds to persist. These regions became targets for further investigation. Spectrometers aboard Clementine, Chandrayaan-1, Kaguya, and Lunar Reconnaissance Orbiter mapped surface composition. Reflected and emitted radiation was compared with laboratory spectra. From this, scientists inferred distributions of plagioclase, pyroxene, olivine, and titanium-rich basalts. Each dataset included calibration standards and uncertainty ranges. Radar observations complemented optical methods. Earth-based radar systems detected strong reflections in polar regions. These signals were consistent with ice mixed into regolith. The L-Cross mission in 2009 tested this interpretation by impacting a crater and analyzing the plume. Instruments detected water vapor and other volatiles. Later missions confirmed these findings. Despite careful documentation, selected results were often simplified in popular accounts. Reports about the Moon ringing after impacts circulated without technical explanation. Internal analyses described material damping and fracture networks. Metaphorical language spread more widely than the underlying data. Density measurements were treated similarly. The Moon's average density is lower than Earth's, reflecting differences in composition and core size. Scientific literature discussed this within formation models. Popular summaries sometimes presented it as unexplained. The numerical values themselves remained stable. Archival records show how these measurements were produced. Telemetry streams were filtered and corrected. Instrument drift was monitored. Cross-checks were conducted using overlapping datasets. Draft papers were revised through correspondence. These procedures were routine and largely invisible outside specialist communities. By the early 21st century, lunar data were integrated into global databases. Researchers combined gravity, topography, chemistry, and age estimates. Some uncertainties narrowed, while others remained. Crustal thickness models depended on density assumptions. Thermal interpretations depended on local geology. Disagreements persisted within accepted ranges. Different modeling approaches produced different outcomes. Review articles documented these variations. Some parameters converged over time, others remained open to revision. Institutionally, the Moon became a reference body. Navigation systems rely on its gravity field. Timekeeping systems depend on its orbit. Physics experiments use its reflectors. Sample collections continue to be re-examined with improved techniques. The accumulated record formed a network of interdependent observations. Seismic signals, gravity anomalies, thermal gradients, and spectral data constrained one another. Adjustments in one parameter affected others. Researchers tracked these relationships through long-term modeling. By the end of the Apollo seismic program and through later orbital missions, the Moon had become one of the most thoroughly measured objects beyond Earth. The main challenge shifted from collecting data to interpreting interconnected systems. The instruments continued to produce numbers that resisted simple explanation: records, archives, and the long memory of missions. From the beginning of lunar exploration, large portions of the work took place far from launch pads and landing sites. In offices, laboratories, and storage facilities, systems were established to manage the growing volume of material produced by each mission. Flight plans, telemetry streams, photographs, voice recordings, engineering diagrams, and scientific measurements were treated as long-term assets. Procedures were designed to ensure that these records could be retrieved and interpreted decades later. During the Apollo program, NASA created dedicated archival structures for lunar data. Mission control transcripts were typed, edited, and bound. Telemetry was stored on magnetic tape and later transferred to newer formats. Engineering drawings were catalogued by part number and revision date. Each astronaut's checklist and notebook was preserved. These materials were distributed across centers in Houston, Huntsville, Pasadena, and Washington, forming a decentralized but coordinated archive. Lunar samples required even stricter documentation. After returning to Earth, rocks and soil were processed at the Lunar Receiving Laboratory in Houston. Each specimen was assigned a number, photographed, weighed, and sealed. Handling procedures limited contamination. Portions were distributed to approved laboratories, while most material was stored in nitrogen-filled cabinets. A duplicate collection was placed in a secure facility at White Sands, New Mexico, as a contingency. Inventory logs were updated continuously. The curation system was designed for long-term use. Researchers requesting samples submitted proposals reviewed by committees. Approved allocations were tracked through detailed paperwork. When portions were returned, they were reweighed and inspected. This process allowed the same material to be studied using different techniques as analytical tools improved. Samples collected in the early 1970s were later examined using methods developed decades afterward. Orbital and surface mission records followed similar preservation practices. Data from Clementine, Lunar Prospector, Kaguya, Chandrayaan-1, and Lunar Reconnaissance Orbiter was stored in digital archives managed by NASA's Planetary Data System and equivalent international repositories. These databases standardized file formats, metadata descriptions, and access rules. Each dataset included information about instrument calibration, processing steps, and known limitations. The Planetary Data System, established in 1989, became a central hub for lunar and planetary records. Its structure divided data into discipline nodes, such as geosciences and atmospheres. Lunar measurements were distributed across these nodes based on content. Users could download raw and processed files, along with documentation. This system reduced dependence on individual research groups and preserved continuity when personnel changed. Older records posed additional challenges. Early Apollo telemetry and video were recorded on formats that later became obsolete. During the 1990s and 2000s, NASA initiated recovery and digitization projects. Engineers searched warehouses and storage vaults for original tapes. Some materials had deteriorated or been reused. Others required custom-built playback equipment. The restoration process involved reconstructing signal chains and reinterpreting documentation. One well-known example involved the Apollo 11 television recordings. Original high-resolution data were transmitted to Earth and converted for broadcast. Many original tapes were later lost or overwritten. In the 2000s, surviving recordings from international tracking stations were located and digitized. These efforts demonstrated both the vulnerability and resilience of technical archives. Scientific correspondence also became part of the record. Letters, memoranda, and draft manuscripts documented how interpretations evolved. University libraries and private collections preserved these materials. Historians of science later used them to trace debates about lunar origin, composition, and internal structure. These documents showed how conclusions were shaped by available data and prevailing models. Institutional memory was reinforced through review volumes and reference texts. Publications, such as the Lunar Sourcebook, released in 1991, compiled decades of findings into standardized summaries. These works cited original reports and provided context for new researchers. Updated editions and digital versions continued this function. They acted as bridges between generations of investigators. Reanalysis became a routine practice. As computing power increased, older datasets were reprocessed using improved algorithms. Gravity data from early missions were combined with Grail measurements. Seismic records were filtered using modern techniques. Spectral data were recalibrated against new laboratory standards. These revisions sometimes altered numerical estimates without changing general conclusions. Sample studies followed a similar pattern. Early analyses focused on basic mineralogy and isotopic dating. Later work applied microprobe analysis, synchrotron radiation, and nanoscale imaging. Tiny inclusions and trace elements became accessible. Some specimens were opened for the first time after decades in storage. Curators coordinated these studies to preserve material for future methods. International cooperation expanded archival practices. Agreements between space agencies facilitated data sharing. Joint repositories were created for missions involving multiple partners. Standards were harmonized to allow cross-comparison. For example, Japanese and Indian lunar datasets were integrated with American and European records. This coordination reduced duplication and increased transparency. Access policies evolved over time. During the Apollo era, many records were restricted. Over subsequent decades, declassification and digitization broadened availability. Online portals replaced physical reading rooms. Students, researchers, and independent analysts could retrieve materials that once required formal requests. This shift changed how lunar research was conducted and reviewed. Despite these systems, gaps remained. Some early documentation was incomplete. Equipment logs were occasionally missing. Personal notes were lost. Budget constraints limited preservation efforts. Archivists documented these deficiencies and attempted partial reconstruction. In some cases, conclusions had to be drawn using indirect evidence. The management of lunar records required continuous maintenance. File formats were updated, storage media were replaced, backup systems were implemented, databases were migrated to new platforms. These activities were rarely visible to the public but essential for long-term usability. Without them, large portions of lunar history would have become inaccessible. Over time, the Moon accumulated not only physical traces of exploration, but also layered documentation. Landing sites, instrument locations, and impact points were mapped alongside filing systems and catalogue numbers. Each mission added new entries to an expanding registry. The Moon became embedded in institutional routines. By the early 21st century, lunar archives supported diverse uses. Scientists relied on them for comparative studies. Engineers consulted them for mission planning. Historians examined them for contextual analysis. Educators used them for instruction. Policy planners referenced them for future programs. All depended on stable records. The long memory of lunar exploration was therefore constructed deliberately. It emerged from coordinated efforts in curation, digitization, and documentation. These practices ensured that measurements and samples remained interpretable across generations. The Moon's scientific history became inseparable from its archival infrastructure, mapping the surface without touching it. For much of modern history, the Moon was studied by people who spent long hours looking through eyepieces, waiting for clouds to pass and shadows to shift. Observers worked at fixed desks, returning night after night to the same craters and plains. They kept handwritten logs, adjusted lenses by touch, and compared new sketches with older ones. These routines were slow and repetitive. Over time, they produced a shared understanding that the Moon could be measured, classified, and mapped through steady attention rather than physical contact. During the 19th and early 20th centuries, major observatories in France, Germany, Britain, and the United States produced systematic lunar surveys. Photographic plates gradually replaced hand drawings. Astronomers such as Julius Schmidt and Maurice Loewy assembled large collections of images taken under different lighting conditions. By comparing shadow lengths and surface textures, they estimated elevations and slopes. Atmospheric distortion limited precision, but these atlases established consistent naming systems and reference grids. A major change occurred when spacecraft began orbiting the Moon. In 1959, the Soviet Luna 3 probe transmitted the first images of the far side. The photographs were grainy and incomplete, but they revealed large basins and unfamiliar terrain. These images forced cartographers to revise existing maps and create new coordinate frameworks. Follow-up lunar missions during the early 1960s improved coverage and resolution. The United States expanded orbital mapping through the Lunar Orbiter program between 1966 and 1967. 5 spacecraft photographed most of the lunar surface. Each carried dual cameras that exposed film, developed it on board, and scanned it for transmission. Engineers reconstructed images from fragmented signals. Motion blur and geometric distortion were corrected through careful processing. The final mosaics represented the most detailed lunar maps available at the time. Lunar orbiter data supported Apollo landing site selection. Analysts examined slopes, boulder fields, and crater densities. These features were evaluated for safety and scientific value. The results were compiled into technical atlases and internal reports. Mapping became closely linked to mission engineering, navigation, and risk assessment. After Apollo, digital imaging replaced film-based systems. Clementine, launched in 1994, carried cameras operating in ultraviolet, visible, and infrared wavelengths. It produced near-global coverage. By comparing reflectance patterns, scientists inferred surface composition. Clementine also enabled early stereo-derived elevation models that improved terrain analysis. Lunar Prospector, launched in 1998, contributed indirectly to mapping. Although it carried no cameras, its gravity and neutron spectrometer data helped relate surface features to subsurface structure. Regions with enhanced hydrogen signatures were matched with topographic maps. This integration supported studies of polar environments and crater interiors. Japan's Kaguya mission, launched in 2007, marked a major advance in topographic measurement. Its laser altimeter recorded precise elevation data across nearly the entire surface. Terrain cameras produced high-quality stereo imagery. Radar sounders probed subsurface layers. These combined datasets allowed researchers to model slopes, fault systems, and buried lava flows. India's Chandrayaan-1 mission, launched in 2008, introduced extensive hyperspectral mapping. The Moon Mineralogy Mapper measured reflected light across hundreds of narrow wavelength bands. This allowed identification of specific minerals and chemical compounds. Absorption features associated with hydroxyl and water molecules were detected and independently verified. NASA's Lunar Reconnaissance Orbiter, launched in 2009, became the main source of high-resolution imagery. Its narrow-angle cameras recorded surface details at sub-meter scales. The wide-angle camera provided global context. The Lunar Orbiter Laser Altimeter collected billions of elevation points. Together, these instruments produced comprehensive digital models of the surface. Elevation data enabled precise measurements of crater depths, rim heights, and basin profiles. Researchers analyzed these features to study impact mechanics and surface modification. Vertical accuracy reached meter-level precision in many regions. These models were combined with gravity and seismic data to improve interior interpretations. Radar mapping complemented optical techniques. Synthetic aperture radar instruments penetrated surface layers and detected roughness variations. Earth-based radar systems at Arecibo and Goldstone provided additional coverage. Radar reflections revealed buried structures and variations in regolith thickness. These results were incorporated into geological maps. Photometric correction became essential for reliable interpretation. Lunar brightness varies strongly with sun angle and viewing geometry. Raw images often reflected lighting conditions rather than composition. Scientists developed correction models to normalize illumination. These adjustments allowed consistent comparison across missions and regions. Surface age estimation relied heavily on crater statistics. High-resolution imagery made accurate crater counting possible. By comparing crater densities with radiometrically dated samples, researchers established relative chronologies. These methods were applied globally and formed the basis of lunar stratigraphy. Geological mapping integrated multiple datasets. Analysts overlaid imagery, elevation models, spectral maps, and gravity fields. Boundaries between surface units were traced digitally. Map products were published by the U.S. Geological Survey and international partners. Each release included metadata describing sources, processing steps, and uncertainties. Cartographic standards evolved alongside data quality. Projection systems were refined. Coordinate reference frames were updated using laser ranging and spacecraft tracking. The International Astronomical Union maintained naming conventions and control networks. These standards ensured compatibility across datasets. Automated analysis became increasingly important. Machine learning tools were applied to crater detection and terrain classification. Large image archives were processed more efficiently. Results were checked against expert interpretations. Automation reduced workload, but did not replace manual verification. Limitations persisted despite improvements. Permanently shadowed regions remained difficult to image optically. Extreme illumination angles distorted some features. Radar penetration varied with material properties. Elevation models depended on orbital coverage. These constraints were documented in technical literature. Mapping also supported operational planning. Landing hazard assessments used slope and roughness data. Rover routes were designed using elevation profiles. Communication planners relied on terrain models to predict signal paths. Each application depended on accurate cartography. Over time, lunar maps became dynamic systems. New missions revised earlier interpretations. feature boundaries were adjusted, databases were updated, printed atlases were replaced by interactive platforms that preserved revision histories. Remote mapping did not replace physical sampling. Instead, it provided context for laboratory analysis and mission design. Samples validated spectral interpretations. Maps guided collection strategies. The two approaches remained linked. The Moon's surface became one of the most thoroughly mapped terrains beyond Earth. Its representation emerged from successive generations of observers, instruments, and processing methods. Each layer added resolution and context without removing earlier records. Interpreting origins through measured patterns. As surface maps and datasets accumulated, researchers began comparing features across wide regions rather than isolated sites. Crater densities, elevation profiles, chemical signatures, and gravity anomalies were examined together. These patterns were treated as records of long-term physical processes. Interpretation relied on statistical methods, laboratory experiments, and comparisons with other planetary bodies. The Moon was analyzed as a system shaped by measurable forces acting over extended periods. One of the earliest interpretive frameworks focused on crater distribution. High-resolution imagery showed that some regions were densely covered with overlapping impact features, while others were relatively smooth. Highlands exhibited heavy crater saturation, while mare regions contained fewer large craters. By comparing these densities with radiometrically dated samples, scientists established relative age sequences. Older surfaces generally contained more craters. Younger volcanic plains showed fewer impacts. This relationship became the basis of lunar stratigraphy. Geological units were classified according to crater frequency and superposition relationships. Features that overlapped others were considered younger. Ejecta blankets were traced to source craters. These methods were adapted from terrestrial geology and refined through orbital data. Over time, standardized lunar time periods were defined and incorporated into reference systems. Chemical measurements provided additional constraints. Sample analysis revealed systematic differences between highland and mare materials. Highlands were dominated by anorthosite rich in calcium and aluminum. Mare basalts contained higher concentrations of iron, magnesium, and titanium. Orbital spectroscopy confirmed these patterns at global scales. The consistency between remote sensing and laboratory data strengthened confidence in compositional interpretations. Isotopic dating played a central role in origin studies. Uranium-lead, potassium-argon, and rubidium-strontium methods were applied to lunar samples. These techniques measured radioactive decay products to estimate formation ages. Results showed that many highland rocks formed more than 4 billion years ago. Mare basalts were generally younger, ranging from about 3 to 4 billion years in age. These findings established a timeline for major geological events. Gravity and topography data contributed to models of early structure. Measurements indicated variations in crust thickness. Highlands tended to have thicker crust than mare regions. Large impact basins showed crustal thinning. These patterns suggested that major collisions and volcanic processes reshaped the Moon's interior. Numerical simulations tested how different formation scenarios could produce such distributions. Seismic data added information about internal layering. Analysis of moonquake records suggested a crust, mantle, and small core. Estimates of core size varied depending on modeling assumptions. Some models included partially molten regions. Others favored mostly solid interiors. These interpretations were constrained by seismic velocities and density estimates derived from gravity measurements. Heat flow data influenced theories of thermal evolution. Low measured heat output implied limited ongoing internal activity. Combined with radiometric ages, this suggested that major volcanic processes occurred early in lunar history. Cooling rates were modeled using known material properties. These models were compared with observed distributions of lava flows and volcanic features. Comparative planetology provided context. Scientists compared lunar data with measurements from Mars, Mercury, and asteroids. Similarities and differences were used to evaluate formation pathways. For example, Mercury's high density and thin mantle contrasted with the Moon's low density and thick crust. Mars exhibited more prolonged volcanic activity. These comparisons helped define boundary conditions for lunar models. One widely studied framework was the giant impact hypothesis. According to this model, a Mars-sized body collided with the early Earth, ejecting material that later formed the Moon. Support for this idea came from isotopic similarities between Earth and Moon rocks, as well as angular momentum considerations. However, details of mixing, cooling, and accretion remained subjects of research. Variations of the model were developed to account for new measurements. Isotopic studies became increasingly important. High-precision analyses showed that oxygen, titanium, and tungsten isotopic ratios in lunar samples closely matched those of Earth. This similarity required explanation within formation models. Some simulations proposed extensive mixing during impact. Others suggested alternative collision geometries. These discussions were documented in technical journals and conference proceedings. Alternative models were also examined. Some researchers explored scenarios involving capture, co-accretion, or multiple impacts. These ideas were evaluated against available data. Most were found inconsistent with observed angular momentum, composition, or age distributions. Nevertheless, they remained part of scientific literature as comparative cases. Surface morphology offered further evidence. Basin rings, concentric fractures, and volcanic rills were mapped and measured. Their dimensions were compared with experimental impact studies and numerical simulations. Results indicated that large basins formed through high-energy collisions. Subsequent magma flooding created smooth plains. These interpretations were supported by gravity anomalies beneath basin floors. Magnetic measurements influenced origin studies as well. Some lunar rocks retained remanent magnetization, indicating the presence of an ancient magnetic field. Orbital magnetometer data revealed localized magnetic anomalies. These findings suggested that the Moon once possessed a core dynamo. Models were developed to explain how such a field could have existed given estimated core size and cooling rates. Sample diversity expanded through later missions. Chang'e 5 returned material from a relatively young basalt region in 2020. Dating showed ages around 2 billion years, younger than most Apollo samples. This extended the known duration of volcanic activity. The new data required revisions to thermal evolution models and crater age calibration curves. Statistical methods became increasingly central. Large datasets were analyzed using probability distributions and error propagation techniques. Uncertainty ranges were explicitly reported. Competing models were evaluated using goodness of fit criteria. These practices reduced reliance on single measurements and emphasized patterns across multiple datasets. Interpretation was influenced by instrument limitations. Resolution, noise levels, and calibration uncertainties affected results. Researchers documented these constraints in methodological sections. Reanalysis often occurred when improved processing techniques became available. Some earlier conclusions were modified as a result. Institutional processes shaped interpretation. Review panels, journal referees, and conference workshops guided consensus formation. Large synthesis papers summarized prevailing views while noting unresolved issues. These documents were periodically updated. Shifts in interpretation were usually gradual rather than abrupt. Public summaries often simplified these complex discussions. Formation models were presented in condensed form, with emphasis on dominant hypotheses. Technical debates over parameters and assumptions received less attention. This created a gap between specialist literature and general descriptions. Within scientific communities, disagreement remained normal. Different research groups favored different modeling approaches. Some emphasized isotopic constraints, others focused on dynamical simulations. These perspectives were debated through publications and collaborative projects. Over time, some disagreements narrowed, while others persisted. Interpretation depended on the continued availability of reliable data. New missions refined existing patterns. Improved laboratory techniques increased measurement precision. Archival preservation ensured access to earlier records. Each new dataset was evaluated in relation to established frameworks. The study of lunar origins therefore developed as an iterative process. Measurements produced patterns. Patterns suggested models. Models were tested against additional observations. Revisions followed when inconsistencies appeared. This cycle repeated across decades. Rather than yielding a single fixed narrative, the accumulated evidence supported a structured range of possibilities bounded by measurable constraints. These boundaries were defined by chemistry, physics, and chronology. Within them, interpretations continued to be refined, from data to public narratives. As lunar research expanded, most technical findings remained confined to journals, conference proceedings, and internal reports. These materials were written for specialists and relied on shared assumptions about terminology, methodology, and statistical practice. Outside these circles, access was limited. Subscription costs, institutional affiliations, and technical language restricted readership. As a result, only a small portion of lunar research reached the general public in its original form. To bridge this gap, intermediary publications played an important role. Review articles, government summaries, and educational reports condensed large bodies of research into standardized formats. Organizations such as NASA's Office of Public Affairs and the National Academy of Sciences produced accessible documents intended for teachers, journalists, and policymakers. These texts translated technical measurements into descriptive language while retaining references to original sources. Textbooks represented another major channel of transmission. Introductory astronomy and planetary science books incorporated lunar findings into structured curricula. Authors selected representative images, diagrams, and datasets. Complex debates were reduced to dominant models and historical sequences. Alternative interpretations were often mentioned briefly or omitted. Each edition reflected the prevailing consensus at the time of publication. Popular science magazines and newspapers further reshaped lunar research. Publications such as Scientific American, National Geographic, and major national newspapers commissioned feature articles on space exploration. Journalists worked with press officers and scientists to produce readable narratives. Technical terminology was replaced with analogies and simplified explanations. Word limits and editorial priorities influenced what could be included. Press releases became central to this process. Space agencies prepared summaries whenever missions released major datasets or published significant results. These documents emphasized novelty, relevance, and clarity. Journalists frequently relied on these releases when preparing stories, especially under tight deadlines. Television and documentary programming introduced additional layers of interpretation. Programs produced by public broadcasters and commercial networks combined archival footage, interviews, and narration. Visual sequences were arranged to maintain audience attention. Scientific uncertainty was often compressed into brief statements. Timelines were simplified. These productions reached wider audiences than printed media. During the Apollo era, televised coverage established early templates for public lunar narratives. Live broadcasts of launches and landings were accompanied by expert commentary. After the missions ended, retrospective programs revisited the material. Editing choices shaped how events were remembered. Emphasis was placed on certain moments and personalities. Museums and science centers also contributed to public interpretation. Exhibitions displayed lunar samples, spacecraft components, and scale models. Curators selected explanatory panels and interactive displays. Content was designed for visitors with limited technical background. Interpretive frameworks emphasized chronological progression and key discoveries. Educational institutions reinforced these narratives. School curricula incorporated simplified accounts of lunar exploration and formation. Lesson plans focused on major milestones and widely accepted models. Assessment standards favored clear, stable explanations. Nuanced debates were generally excluded from early education. With the expansion of digital media in the late 20th and early 21st centuries, dissemination patterns changed. Space agencies created online archives and multimedia platforms. Universities published open access papers. Independent websites summarized research findings. Social media accounts shared images and short explanations. These channels increased access while reducing editorial filtering. Search engines and recommendation algorithms influenced which lunar topics gained visibility. Highly illustrated content and easily summarized claims were favored. Technical caveats and statistical discussions attracted less attention. Over time, repeated exposure reinforced certain themes and framings. Simplification was not inherently inaccurate, but it involved selection. Journalists and educators chose which findings to highlight. Parameters, error margins, and methodological debates were often removed. What remained were streamlined narratives that prioritized coherence over completeness. One recurring example involved impact chronology. Technical literature discussed uncertainties in crater dating. Popular accounts presented fixed timelines. Another involved isotopic analysis, where complex laboratory procedures were reduced to statements about similarity or difference. These transformations reflected practical communication constraints. Interviews with scientists formed another important channel. Researchers were asked to summarize years of work in short segments. Responses were shaped by time limits and audience expectations. Careful phrasing in academic papers was replaced by conversational language. Context was sometimes lost. Institutional communication strategies influenced presentation. Funding agencies emphasized societal relevance. Space agencies highlighted exploration goals. Universities promoted research prestige. These priorities shaped press materials and public statements. Documentary filmmakers and authors occasionally consulted archival sources directly. Some productions incorporated excerpts from original reports and mission logs. Others relied mainly on secondary summaries. Differences in sourcing affected depth and accuracy. Public narratives also reflected cultural conditions. During periods of heightened interest in space, coverage increased. During budgetary downturns, attention declined. Shifts in political priorities influenced emphasis on human versus robotic missions. These factors altered how lunar research was framed. Over time, certain images and phrases became standard. Photographs of Earth rising over the lunar horizon, boot prints in regolith, and statements about ancient impacts were repeated across media. Repetition created familiarity. Familiarity encouraged acceptance. Discrepancies between specialist and public accounts were documented by historians and sociologists of science. Studies examined how uncertainty was communicated and how consensus was constructed. These analyses showed that simplification followed recognizable patterns. Public understanding of lunar science therefore emerged from layered communication systems. Data moved from instruments to papers, from papers to reviews, from reviews to media, and from media to education. At each stage, content was condensed and reorganized. This process did not eliminate technical literature. Specialist communities continued to operate independently. However, most non-specialists encountered the moon through mediated narratives rather than primary data. The result was a dual record. One consisted of calibrated measurements, archived datasets, and peer-reviewed models. The other consisted of accessible stories, timelines, and visual summaries. Both drew from the same sources but served different functions: anomalies, misreadings, and persistent claims. Many of the claims that later circulated about the moon did not originate in laboratories or mission control rooms. They emerged gradually through informal retellings, short quotations, and repeated summaries. A sentence from a report might appear in an interview, then in a magazine article, and later in an online forum. Each step shortened the original explanation. Over time, fragments of technical language began to function independently of their original sources. One frequently cited example involved seismic recordings from Apollo missions. During controlled impact experiments, spent rocket stages were guided to strike the lunar surface. Seismometers recorded extended vibrations. Internal reports attributed this behavior to low energy loss in dry, fractured rock. Engineers and geophysicists described the effect in formal terms related to attenuation and scattering. In later retellings, the phrase "rang like a bell" appeared. Without its technical context, this description was interpreted as evidence of unusual internal structure. Density measurements followed a similar path. The moon's average density is lower than Earth's, reflecting differences in composition and core size. Scientific papers treated this value as one variable within formation models. In non-specialist discussions, the same number was often presented as inherently mysterious. Comparisons were made without reference to material properties or internal layering. The original calculations remained unchanged, but their explanatory framework was removed. Gravity anomalies, particularly mass concentrations beneath impact basins, were also reinterpreted. Apollo-era tracking data revealed small variations in spacecraft motion. These were analyzed and linked to dense basalt deposits. Technical literature documented the modeling process in detail. Outside specialist circles, mascons were sometimes described as unexplained features. The decades of supporting analysis were rarely mentioned. Photographic imagery became another source of reinterpretation. High-resolution images showed shadows, ridges, and irregular textures. Under certain lighting conditions, natural formations appeared geometric. In some cases, these features were described as artificial structures. Subsequent studies traced such impressions to illumination geometry, resolution limits, and image compression. These explanations were published in technical reports but circulated less widely than the initial claims. Audio recordings from Apollo missions were also selectively quoted. Mission transcripts contain extensive procedural communication. Short expressions of surprise or uncertainty were sometimes isolated. In context, these remarks referred to routine observations or equipment behavior. Removed from surrounding dialogue, they appeared ambiguous. Full transcripts were publicly available, but excerpts were more frequently reused. Radar and reflectivity measurements produced similar misunderstandings. Strong radar reflections in polar regions were interpreted by scientists as consistent with ice-bearing regolith. Some popular accounts described these signals as evidence of concealed structures. Later impact experiments and spectroscopic studies confirmed the presence of volatiles. The technical basis for these conclusions was well documented, but simplified interpretations persisted. Magnetic anomalies provided another example. Orbital magnetometers detected localized regions of remnant magnetization. Researchers linked these to ancient impact events and cooling histories. Laboratory measurements supported these interpretations. In some informal discussions, however, the anomalies were described as engineered materials. Geological explanations were less frequently cited. Surface age estimates were occasionally misrepresented. Crater count dating involves statistical uncertainty and calibration against sample ages. Technical papers present age ranges and confidence intervals. Popular summaries sometimes converted these into fixed dates. Differences between estimates were treated as contradictions rather than methodological variations. Historical documents were often cited without regard to revision. Early papers from the 1960s and 1970s expressed uncertainty due to limited data. Later studies refined these conclusions. In some discussions, early speculative statements were presented as current evidence. Updates and corrections were ignored. The development of knowledge over time was compressed into a single moment. Translation and paraphrasing introduced additional distortion. Reports written in Russian, Japanese, and German were summarized in English-language sources. Technical terms were simplified. Nuances were lost. Secondary translations amplified minor ambiguities. These versions sometimes circulated independently of the originals. Selective citation reinforced these processes. Passages that appeared unusual were repeated across books, websites, and videos. Explanatory sections were omitted. This produced chains of references in which the same fragment appeared in multiple sources. Tracing claims back to primary documents became difficult. Digital platforms intensified these patterns. Search engines favored frequently shared content. Visual material and brief statements gained prominence. Corrections and clarifications spread more slowly. As a result, simplified interpretations reached wider audiences than detailed analyses. Some persistent claims originated in misunderstandings of technical terminology. Words such as void, anomaly, and signal have specific meanings in geophysics. In informal usage, they were interpreted literally. For example, void in seismic modeling refers to low-density regions, not empty spaces. Such distinctions were rarely preserved in popular explanations. Institutional responses addressed these issues intermittently. NASA and academic organizations published clarifications and educational resources. Outreach programs explained data processing methods. These materials competed with a larger volume of unmoderated content. Their visibility was limited. Historians and sociologists of science documented similar patterns in other fields. Studies showed that provisional statements were often treated as permanent conclusions. Technical uncertainty was transformed into perceived mystery. Corrections received less attention than initial reports. Within research communities, anomalies were treated differently. Unexpected results were investigated through replication and modeling. Alternative explanations were tested. Findings were revised when necessary. This process was visible in journals and conference proceedings. Outside these venues, the same anomalies were sometimes treated as unresolved facts. Many recurring lunar claims did not depend on new evidence. They circulated for decades with little modification. Their persistence reflected communication practices rather than observational support. Archival records showed that relevant data had been available throughout this period. Researchers continued to publish comprehensive reviews addressing these issues. Seismic behavior, gravity models, and compositional data were summarized in detail. These works provided context for earlier measurements. They were widely cited in specialist literature, but rarely referenced in informal discussions. Educational initiatives attempted to reduce misunderstandings. University courses and public lectures emphasized data interpretation. Open access publishing increased availability. Despite these efforts, simplified narratives remained prominent. The divergence between technical and popular interpretations produced parallel traditions. One relied on calibrated measurements and peer review. The other relied on repetition and selective emphasis. Both referred to the same missions and instruments but followed different standards. The history of lunar anomalies therefore reflects broader patterns in information transmission. Observations were recorded precisely. Interpretations were debated and revised. Simplified versions circulated independently. Over time, fragments detached from their sources and acquired separate meaning, rechecking the Moon in a new era of missions. After the end of the Apollo program, direct human activity on the Moon ceased. But scientific interest did not decline. Instead, space agencies shifted toward robotic exploration and long-term observation. Advances in electronics, computing, and sensor technology made it possible to revisit earlier measurements with improved precision. New missions were designed to verify, extend, and refine data collected during the 20th century. During the 1990s, renewed lunar exploration began with relatively low-cost spacecraft. The Clementine mission in 1994 produced multispectral imagery and gravity estimates. Its data were used to test compositional models derived from Apollo samples. 4 years later, Lunar Prospector mapped gravity and neutron emissions. The detection of enhanced hydrogen near the poles prompted focused studies of permanently shadowed regions. These early missions demonstrated the value of systematic re-examination. In the 2000s, international participation expanded. The European Space Agency's SMART 1 mission, launched in 2003, tested solar electric propulsion while conducting infrared and X-ray observations. SMART 1 mapped elemental abundances and surface composition. Its datasets were compared with Clementine and Apollo results, revealing broad consistency and improved spatial resolution. Japan's Kaguya mission, launched in 2007, carried 14 instruments dedicated to topography, imaging, and subsurface sounding. Its laser altimeter refined elevation models. Radar sounders probed buried lava flows. Gravity measurements improved understanding of crustal thickness. Kaguya data were used to reassess basin formation models and volcanic history. India's Chandrayaan-1 mission, launched in 2008, added high-resolution hyperspectral mapping. The Moon Mineralogy Mapper detected absorption features associated with hydroxyl and water molecules. These findings were cross-checked with neutron and radar data. Subsequent analyses confirmed that surface hydration varies with latitude and illumination conditions. NASA's Lunar Reconnaissance Orbiter, launched in 2009, provided continuous high-resolution coverage. Its cameras documented changes in lighting, surface disturbances, and impact events. The Lunar Orbiter Laser Altimeter produced precise topographic profiles. These measurements refined slope estimates, crater depth calculations, and basin morphology. In 2011, the Grail mission produced detailed gravity maps. By measuring variations in spacecraft separation, researchers mapped internal mass distribution. These results were compared with seismic and topographic data. Models of crustal structure were updated accordingly. Grail confirmed earlier findings about basin-related mass concentrations and crustal thinning. Targeted impact experiments also contributed to verification. The LCROSS mission in 2009 deliberately struck a polar crater. Instruments analyzed the resulting plume. Water vapor and volatile compounds were detected. These measurements supported earlier, indirect evidence from neutron spectroscopy and radar. Sample return missions provided additional opportunities for comparison. China's Chang'e 5 mission in 2020 returned material from Oceanus Procellarum. Laboratory analysis dated these basalts to about 2 billion years old. This extended the known period of lunar volcanism. The results were integrated into crater age calibration systems. Later missions continued this approach. Chang'e 4, which landed on the far side in 2019, deployed instruments to study surface composition and radiation environment. Data were compared with near-side measurements. Differences and similarities were documented in peer-reviewed studies. Advances in data processing enabled more detailed reanalysis. Improved algorithms, reduced noise, and corrected earlier calibration errors. Archival datasets were reprocessed using updated software. Gravity, spectral, and thermal data from multiple missions were merged into unified models. These procedures often reduced uncertainties without changing overall interpretations. High-performance computing supported large-scale simulations. Impact modeling, thermal evolution studies, and orbital dynamics calculations were refined. New computational results were tested against observational records. Discrepancies prompted further measurement and revision. Continuous monitoring also improved temporal understanding. Repeated imaging allowed detection of small surface changes caused by micrometeorite impacts and thermal stress. Newly formed craters were catalogued. These observations refined estimates of current impact rates and surface turnover. Laser ranging experiments continued throughout this period. Upgraded observatories improved timing accuracy. Long-term records were analyzed for subtle variations in orbital parameters. These studies confirmed earlier measurements and constrained tidal evolution models. Institutional collaboration increased. Joint missions and data-sharing agreements facilitated cross-validation. International working groups compared results from different instruments. Standardized calibration references were developed. These practices reduced systematic discrepancies. Mission planning increasingly emphasized verification. Instruments were designed with overlapping capabilities. Redundant measurements allowed internal consistency checks. For example, surface composition was examined using both spectroscopy and in situ analysis. Topography was measured using laser altimetry and stereo imaging. Educational and archival initiatives supported rechecking efforts. Digital repositories preserved raw and processed data. Documentation of processing methods was expanded. This allowed independent researchers to replicate analyses. Transparency became a formal requirement for many projects. Not all earlier results were confirmed without modification. Some estimates of crust thickness, heat flow, and volatile abundance were adjusted. Error ranges were revised. These changes were documented in review papers. Revisions reflected improved resolution rather than fundamental contradictions. Public communication accompanied these missions. Press releases emphasized continuity with earlier exploration. Scientists highlighted how new data refined existing knowledge. Comparisons with Apollo-era findings were common. These narratives reinforced the cumulative nature of lunar research. The renewed exploration era demonstrated that earlier measurements remained broadly reliable. Modern instruments increased precision and coverage. They clarified uncertainties and extended temporal and spatial ranges. Each mission added incremental detail. By combining robotic exploration, advanced analysis, and archival preservation, researchers maintained a continuous process of verification. Its study illustrated how scientific conclusions are revisited and refined over generations. Institutional continuity and the shape of consensus. Lunar research has never been conducted by isolated individuals working independently. From the earliest space missions onward, it has been organized through agencies, laboratories, universities, and international partnerships. These institutions established the procedures by which data were collected, evaluated, and accepted. Over time, stable organizational structures influenced how interpretations were developed and maintained. During the Apollo era, most lunar research in the United States was coordinated through NASA centers and affiliated universities. Funding was distributed through competitive grants reviewed by panels of specialists. Research priorities were set through advisory committees and long-range planning documents. Similar structures existed in the Soviet space program, where institutes of the Academy of Sciences supervised lunar studies. These arrangements shaped which questions were emphasized and which methods were supported. After Apollo, responsibility for lunar science shifted toward long-term research programs. NASA's Planetary Science Division managed mission selection, data archiving, and grant distribution. Proposal review systems were formalized. Researchers were required to document objectives, methodologies, and expected outcomes. These procedures promoted standardization and reproducibility. Comparable systems developed within the European, Japanese, Chinese, and Indian space agencies. Peer review became central to consensus formation. Submitted papers were evaluated for methodological rigor, data quality, and consistency with existing literature. Revisions were often required before publication. Through this process, unsupported interpretations were filtered out. Findings that survived multiple rounds of review gained greater credibility. Professional societies reinforced these norms. Organizations such as the American Geophysical Union and the Division for Planetary Sciences organized annual meetings. Researchers presented preliminary results, received feedback, and compared interpretations. Conference proceedings and abstract volumes documented evolving viewpoints. Repeated presentation and discussion contributed to convergence around certain models. Large synthesis projects played a coordinating role. Review papers, assessment reports, and reference volumes summarized accumulated evidence. These works were often produced by committees representing multiple institutions. Drafts circulated for comment. Disagreements were negotiated through revisions. Final documents reflected shared positions while noting unresolved issues. Graduate training also influenced continuity. Students learned standard analytical techniques and theoretical frameworks. Doctoral programs emphasized familiarity with established datasets and modeling tools. Advisors transmitted research traditions to successive generations. This educational structure promoted stability in methodological approaches. Funding patterns affected interpretive trends. Agencies prioritized projects aligned with strategic goals, such as sample return, polar exploration, or resource assessment. Proposals addressing these themes were more likely to receive support. Over time, clusters of research developed around funded topics. Areas with limited funding progressed more slowly. Mission selection processes reinforced consensus. Instruments were chosen based on expected scientific return and compatibility with existing knowledge. Proposals that fit established frameworks were easier to justify. Novel approaches required additional evidence. This dynamic favored incremental advancement over radical reinterpretation. Data standards further shaped interpretation. Archival systems required consistent formatting and metadata. Calibration procedures were standardized. Shared software tools were developed for processing and analysis. These technical norms reduced variability in results and facilitated comparison across studies. International collaboration introduced additional layers of coordination. Joint missions required agreement on objectives, instrumentation, and data sharing. Working groups established common reference frames and nomenclature. Cross-agency review committees evaluated progress. These mechanisms promoted alignment among national programs. Consensus did not emerge instantly. Competing models were often debated for years. Differences persisted over parameters such as core size, impact chronology, and volcanic duration. Resolution usually occurred through accumulation of independent evidence rather than formal decisions. Over time, models that best accommodated multiple datasets gained wider acceptance. Institutional memory played an important role. Senior researchers served on advisory boards and review panels. Their experience informed evaluation of new proposals. Historical awareness helped prevent repetition of earlier errors. Archives preserved records of past debates and resolutions. Disagreement remained an accepted feature of lunar science. Journals published alternative interpretations when supported by data. Workshops were organized to address unresolved questions. Special issues focused on contested topics. These forums allowed controlled exploration of uncertainty. Publications also reflected institutional influence. High-impact journals favored studies with broad relevance and strong methodological foundations. Specialized journals supported detailed technical work. Review articles were often commissioned from established researchers. Visibility and reputation affected how findings were received. Infrastructure investments reinforced continuity. Laboratories developed specialized equipment for isotope analysis, spectroscopy, and microscopy. Maintaining these facilities required sustained funding. Research programs tended to build on existing capabilities. Shifts in infrastructure could redirect scientific focus. Advisory committees periodically reassessed priorities. Decadal surveys and strategic roadmaps outlined future directions. These documents were produced through extensive consultation. Recommendations guided mission planning and grant allocation. They linked scientific goals with institutional capacity. Consensus formation was therefore distributed across multiple mechanisms: peer review, funding systems, training programs, and collaborative networks operated simultaneously. No single body determined accepted interpretations. Agreement emerged through repeated evaluation and cross-checking. This process favored interpretations that were compatible with diverse datasets and institutional expectations. Models that required fewer exceptions and aligned with established measurements were more easily integrated. Over time, they became reference points for further research. Revisions occurred when new evidence accumulated. Improved measurements prompted updates to earlier conclusions. Institutions adapted by supporting new analyses and missions. Change was typically gradual and documented through successive publications. The structure of lunar science thus combined stability with flexibility. Organizational routines preserved continuity. Open publication and debate allowed adjustment. Together, these features shaped how knowledge about the Moon was consolidated and revised. Revisiting the question of artificial construction. Long after extensive measurements had been collected and archived, discussions about whether the Moon might be artificial continued to circulate in books, lectures, and online forums. These discussions rarely began with new data. Instead, they were built from previously published fragments, quotations, and images. Over time, these materials formed recurring storylines that existed alongside institutional research without intersecting directly with it. Early expressions of artificial construction ideas appeared in the middle of the 20th century, when detailed lunar information was limited. Writers pointed to the Moon's size relative to Earth, its nearly circular orbit, and its role in stabilizing Earth's rotation. These features were described as uncommon. At that stage, few physical measurements were available to evaluate such statements. As lunar exploration progressed, these early claims remained in circulation. During the Apollo period, seismic experiments and sample studies became central reference points. Controlled impacts produced extended vibrations. Internal technical reports explained this behavior using models of fractured, dry rock. Laboratory experiments supported these interpretations. In later retellings, simplified phrases were separated from their scientific context and treated as indicators of hollow spaces or engineered interiors. Measurements of mass and density were also frequently cited. Data showed that the Moon has a relatively small metallic core and lower average density than Earth. Geophysical models explained these features through formation and cooling processes. These models were supported by gravity mapping, seismic analysis, and geochemical evidence. In alternative narratives, the same measurements were presented without reference to these supporting frameworks. Surface imagery provided another source of reinterpretation. High-resolution photographs revealed straight ridges, angular shadows, and polygonal fracture patterns. Geological mapping identified these as tectonic features, lava channels, and impact-related structures. Photometric studies demonstrated how lighting conditions altered appearance. In popular media, selected images were sometimes described as architectural forms. Follow-up analyses documented how viewing geometry produced such effects. Claims about internal cavities were evaluated through multiple independent methods. Seismic wave propagation, gravity field measurements, and rotational dynamics constrained internal structure. Models consistently indicated layered composition with moderate density variations. Large-scale voids compatible with artificial construction were not detected. These findings were reported in geophysical journals and confirmed through later missions. Orbital behavior was another focus of attention. The Moon's synchronous rotation, gradual recession from Earth, and long-term stability were modeled using classical mechanics and numerical simulations. Laser-ranging data spanning decades supported these models. Predictions from artificial placement scenarios were not observed. Orbital parameters matched natural tidal evolution. Isotopic studies provided strong constraints. High-precision analyses showed close similarities between Earth and Moon isotopic ratios for oxygen, titanium, tungsten, and other elements. Formation models incorporated these results through high-energy impact and mixing processes. Artificial construction hypotheses did not offer quantitative explanations for these patterns. Peer-reviewed literature emphasized this limitation. Magnetic and thermal measurements were also relevant. Some lunar rocks preserved evidence of an ancient magnetic field. Orbital surveys revealed localized magnetic anomalies. Heat flow probes recorded low internal energy output. These observations were integrated into models of core evolution and cooling history. No indications of large-scale engineering processes were supported. Institutional responses to artificial construction claims were usually indirect. Review articles summarized relevant measurements without addressing speculative interpretations. Educational materials emphasized established formation models. Public outreach programs focused on explaining data collection and analysis methods rather than debating alternative narratives. Some researchers discussed these topics in interviews and public lectures. Their explanations emphasized reproducibility, error margins, and independent verification. They described how multiple datasets converged on similar conclusions. Artificial construction claims were framed as unsupported by measurable evidence. Social scientists examined why such ideas persisted. Studies showed that they often spread through informal networks, popular media, and online platforms. Repetition and selective quotation reinforced them. Limited engagement with primary sources contributed to their longevity. Archival research traced the development of specific claims. Early speculative remarks were repeatedly paraphrased. Later discoveries were incorporated selectively. Contradictory evidence was excluded. Over time, narratives became increasingly detached from original documents. Digital media accelerated these processes. Video sharing platforms, blogs, and discussion boards favored brief, visually striking content. Simplified interpretations achieved greater visibility. Recommendation systems amplified popular material regardless of accuracy. Within scientific communities, evaluation remained grounded in measurement. New observations were compared with established models. Anomalies were investigated through replication and simulation. Hypotheses were assessed quantitatively. Artificial construction scenarios did not generate testable predictions consistent with observed constraints. Recent missions reinforced these patterns. Chang'e 5 samples, updated gravity surveys, and improved seismic analyses refined understanding of lunar structure. These results were incorporated into review papers. None required reconsideration of artificial origin hypotheses. Educational programs addressed misconceptions indirectly. Courses emphasized planetary formation and data interpretation. Students learned to evaluate claims using evidence and modeling. This training reinforced methodological standards. The question of artificial construction, therefore, remained outside mainstream lunar science. It was not excluded by regulation, but by lack of empirical support. Institutional mechanisms favored explanations compatible with multiple independent measurements. Researchers also recognized that public interest in such ideas reflected broader issues of access and communication. Outreach initiatives emphasized open data and transparency. Online repositories allowed independent examination of mission records. The continued circulation of artificial construction claims did not alter research priorities. Missions focused on geological and physical questions. Instrument development emphasized precision and coverage. Evaluation procedures remained unchanged. By the early 21st century, multiple independent datasets constrained lunar origin and structure. Seismology, geochemistry, gravity, and orbital dynamics formed an interconnected framework. Within this framework, artificial construction hypotheses lacked quantitative foundation. Their persistence reflected patterns of information transmission rather than unresolved scientific problems. Institutional practice continued to rely on calibrated measurement, peer review, and cumulative verification. Public memory, digital archives, and future reinterpretation. By the early 21st century, most primary records of lunar exploration had been converted into digital form. Mission reports, telemetry files, photographs, audio recordings, and sample catalogues were stored in online repositories. Access no longer depended on physical location or institutional affiliation. Researchers, students, and members of the public could retrieve material from personal computers. NASA's planetary data system became a central archive for robotic and crewed mission data. It organized information by discipline and mission. Each dataset included documentation describing instrument calibration, processing steps, and known limitations. International partners maintained parallel systems. These repositories were designed to support long-term use rather than short-term publication. Historical records were also digitized. Apollo mission transcripts, flight plans, and engineering diagrams were scanned and indexed. University libraries and national archives created searchable collections. Private organizations preserved film footage and broadcast material. These efforts reduced dependence on aging physical media and protected records from deterioration. Digital preservation required ongoing maintenance. File formats were updated, storage systems were replaced, redundant backups were created, metadata standards were revised, archivists monitored data integrity. Without these practices, large portions of lunar history would have become inaccessible despite initial digitization. Public access expanded through web platforms. Space agencies developed educational portals that combined images, maps, and explanatory text. Interactive tools allowed users to explore landing sites, orbital tracks, and sample locations. Virtual globes and three-dimensional models became common features of outreach websites. Open access publishing increased availability of scientific literature. Many journals made articles freely available after embargo periods. Preprint servers allowed early dissemination. Institutional repositories hosted accepted manuscripts. These practices reduced barriers between specialist and non-specialist audiences. Social media introduced new forms of engagement. Images from Lunar Reconnaissance Orbiter and other missions were shared widely. Short explanations accompanied photographs. Hashtags and reposting mechanisms amplified selected content. Visual material often received more attention than methodological detail. Digital platforms also facilitated independent analysis. Amateur researchers downloaded datasets and applied custom software. Some produced alternative maps and visualizations. Others attempted reanalysis of published results. While most lacked access to specialized calibration tools, their work reflected increased technical literacy among non-professionals. Online forums and collaborative projects supported collective interpretation. Participants compared sources, exchanged translations, and assembled timelines. Disagreements were discussed publicly. Archival links were shared. These practices created informal peer review environments distinct from academic journals. Search engines influenced which lunar materials were most visible. Frequently visited pages appeared prominently in results. Highly illustrated or simplified explanations gained priority. Technical documentation, often buried in repositories, required targeted searches. Digital archives also preserved conflicting narratives. Official reports, journal articles, personal memoirs, and speculative writings coexisted in searchable form. Users encountered multiple interpretations simultaneously. Evaluating reliability required familiarity with source types and publication contexts. The permanence of online records affected reinterpretation. Early articles and forum posts remained accessible long after publication. Corrections and updates did not always replace earlier versions. Outdated information continued to circulate. This created layered histories within digital spaces. Educational institutions adapted to these conditions. Courses incorporated online datasets and visualization tools. Students learned to navigate archives and assess source credibility. Assignments emphasized comparison of primary and secondary materials. These practices addressed the changing information environment. Museums and research centers expanded digital outreach. Virtual exhibitions presented curated collections of lunar artifacts and documents. High-resolution scans allowed detailed examination. Audio archives preserved mission communications. These resources complemented physical displays. Citizen science initiatives also emerged. Projects invited volunteers to classify craters or annotate images. Participants contributed to research databases under professional supervision. These programs integrated public activity into formal scientific workflows. Policy decisions influenced digital preservation. Funding allocations determined archive maintenance and software development. International agreements addressed data sharing and intellectual property. These frameworks supported continuity. Future reinterpretation depended on data accessibility. As analytical techniques advanced, older records gained new relevance. Machine learning and advanced simulation methods were applied to historical datasets. Digitization enabled such reuse. Archival transparency supported verification. Researchers could trace results back to raw measurements. Processing histories were documented. This reduced reliance on secondary summaries. Independent replication became more feasible. At the same time, information overload posed challenges. The volume of available material increased steadily. Locating relevant sources required filtering skills. Automated recommendation systems influenced discovery patterns. These systems shaped research and public inquiry. Digital preservation also raised ethical and legal questions. Privacy considerations affected some personnel records. Copyright restrictions limited access to certain media. Negotiations determined what could be released. These constraints influenced archival completeness. Public memory of lunar exploration became increasingly mediated through screens and databases. Iconic images were reused in new contexts. Mission events were commemorated through online anniversaries and retrospectives. Narratives were reinforced through repetition. The coexistence of comprehensive archives and fragmented attention defined the new environment. Detailed records were available, but engagement was uneven. Some users explored primary data, others relied on summaries and visual highlights. Over time, digital infrastructures became integral to lunar science and history. They connected past missions with future projects. They supported verification, reinterpretation, and education. Preservation became an ongoing process rather than a completed task. The Moon's modern record thus consisted of layered digital traces. Measurements, maps, correspondence, and narratives were stored side by side. Their interaction shaped how future generations would understand earlier exploration, the continuing cycle of measurement and meaning. Each generation of lunar research has been shaped by the tools available at the time. Telescopes, film cameras, spectrometers, digital sensors, and laser ranging systems, each defined what could be observed and recorded. As instruments changed, so did the types of questions that could be asked. Older datasets did not disappear. They remained in archives, available for reinterpretation using new methods. Modern lunar missions are designed with this continuity in mind. Spacecraft now carry multiple instruments that observe the same regions in different ways. Imaging systems operate alongside spectrometers, altimeters, and particle detectors. Redundant measurements allow internal consistency checks. Data pipelines are built to preserve raw signals as well as processed products. Documentation accompanies each stage of analysis. Sample analysis continues to follow similar principles. Material returned during the Apollo era is still stored under controlled conditions. Portions are released selectively for new studies. Advances in microscopy, mass spectrometry, and imaging allow researchers to examine features that were previously inaccessible. Measurements made decades apart are compared to track analytical improvement. Recent missions emphasize long-duration monitoring. Orbiters remain operational for many years. Instruments record seasonal changes in illumination, temperature, and surface activity. Small impact events are documented through repeated imaging. Radiation environments are measured continuously. These records extend earlier time series and reduce reliance on isolated observations. Computational methods have become increasingly central. Large datasets are processed using automated pipelines. Statistical modeling incorporates uncertainty, estimation, and sensitivity analysis. Simulations of impacts, thermal evolution, and orbital dynamics are refined using high-performance computing. Results are compared against archival measurements. Discrepancies are examined through iterative adjustment. Machine learning techniques are applied to image classification and feature detection. Crater catalogs are generated automatically and reviewed manually. Terrain segmentation identifies geological units. Pattern recognition tools assist in spectral interpretation. These methods accelerate analysis while preserving human oversight. International coordination supports cumulative interpretation. Data sharing agreements ensure that measurements from different agencies are compatible. Joint working groups define calibration standards. Collaborative publications combine datasets from multiple missions. These practices reduce fragmentation and promote comparative analysis. Educational structures adapt to these conditions. Graduate programs emphasize data literacy and archival navigation. Students learn to work with legacy datasets alongside new measurements. Training includes instruction in reproducibility, documentation, and version control. These skills support long-term continuity. Public engagement also evolves. Interactive platforms allow users to explore maps and measurements directly. Visualization tools display gravity fields, elevation models, and mineral distributions. Educational materials increasingly link summaries to primary sources. This approach encourages independent verification. At the same time, communication constraints remain. Technical documentation is extensive. Many users rely on summaries. The balance between accessibility and completeness continues to shape public understanding. Institutions respond by producing layered resources that range from introductory explanations to detailed archives. Funding structures influence this cycle. Mission planning documents emphasize data preservation and reuse. Grant programs support reanalysis projects. Infrastructure investments maintain repositories and processing systems. These commitments sustain long-term interpretive capacity. Policy frameworks reinforce these practices. International guidelines address data, stewardship, and open access. Space agencies incorporate archival requirements into mission design. Review panels evaluate preservation strategies alongside scientific objectives. These measures embed continuity into institutional routines. New measurements often revise earlier estimates without replacing them entirely. Crust thickness models are refined. Volatile abundance maps are updated. Thermal histories are adjusted. Each revision is documented in relation to prior work. Change is recorded rather than obscured. Disagreements remain part of this process. Different modeling approaches yield different parameter values. Assumptions about material properties affect outcomes. Researchers publish alternative interpretations supported by evidence. These differences are tracked through citations and reviews. Long-term datasets provide reference points. Laser-ranging records span more than 5 decades. Seismic archives preserve early measurements. Sample inventories maintain provenance information. These resources anchor interpretation across generations. Technological obsolescence is managed through migration and emulation. Old file formats are converted. Playback equipment is reconstructed when necessary. Software environments are preserved through virtualization. These efforts maintain access to original signals. Future missions are planned within this framework. Sample return projects, polar landers, and human exploration initiatives incorporate archival objectives. Instruments are selected for compatibility with existing records. Data management plans emphasize longevity. The relationship between measurement and meaning remains iterative. Instruments generate numbers. Analysts organize patterns. Models propose explanations. New observations test those models. Revisions follow. This sequence repeats across decades. Cultural factors influence interpretation. Public interest rises and falls. Media attention shifts. Educational priorities change. These conditions affect which findings receive emphasis. Institutional archives preserve less visible material for later use. Historians and sociologists continue to study these processes. They examine how consensus forms, how uncertainty is managed, and how narratives evolve. Their work becomes part of the lunar record alongside scientific publications. The Moon itself remains physically unchanged by these activities. Its surface retains impact, scars, and volcanic plains. Instruments and landing sites mark specific moments in exploration history. These material traces coexist with expanding digital documentation. Over time, layers of observation accumulate. Telescopic sketches, orbital photographs, spectral maps, gravity models, and laboratory analyses form interconnected records. Each layer reflects its technological context. None is fully superseded. Interpretation depends on this layered structure. Understanding emerges from comparison across methods and eras. Contradictions prompt investigation. Convergences reinforce confidence. Meaning is negotiated through repeated measurement. No single dataset determines interpretation. Seismology, geochemistry, imaging, and orbital dynamics constrain one another. Models that satisfy multiple constraints persist. Others are modified or abandoned. This selection process is continuous. Public and specialist traditions remain distinct but interconnected. Technical communities prioritize calibration and replication. Public narratives prioritize coherence and accessibility. Digital archives allow movement between these domains. Future reinterpretation will follow similar patterns. New instruments will generate new perspectives. Old records will be revisited. Analytical standards will evolve. Archives will be reorganized. Earlier conclusions will be reassessed. The history of lunar study, therefore, does not progress toward a final statement. It proceeds through ongoing measurement, comparison, and documentation. Each stage adds detail and context without closing inquiry. The Moon continues to function as a reference object for planetary science. Its long-term observation demonstrates how knowledge is constructed through sustained institutional effort. Measurements acquire meaning through repeated use. In this continuing cycle, data and interpretation remain linked. Instruments, archives, and communities interact over time. Through this interaction, understanding is maintained, revised, and extended. Thanks for watching. If you enjoyed this, hit like, subscribe for more deep dives, and let us know in the comments what you think about the Moon.